anyways, all the materials that I'm going to talk about today come from that book. And I'm going to link you to the chapters at the end that I'm talking about today. So everything I talk about, I'm going to go through it kind of fast just to give you an overview of these things. But if you want to read about them in more detail, the chapters aren't overlong and they're very digestible. And I personally think they're written pretty well. They give like a really good explanation for how we do stats with networks, because network contexts are very different than working with traditional individual level attribute type data that we're used to working with, where we have student characteristics, demographics, test scores, next student, next student, next student. It's more about those relations between students. So when we're doing stats with networks, we just by default violate a ton of just traditional assumptions for statistical analysis. Let's see, Sonmi, not to put you on the spot, but you're talking about like stats earlier. Can you think of like one traditional assumption that we make when we're doing traditional stats that we would violate with network data?
Sorry.
Oh, you're fine. And anybody who wants to respond to it, and I'll give you a clue.
Normality?
Normality, absolutely.
Independence.
Yep. Independence is like the main one, because we're saying like these outcomes aren't independent of each other. In fact, these outcomes that we're looking for students, whether it's like student achievement or sense of belonging or whatever outcome of interest we care about, is in fact totally dependent on other students within this context, and in some cases like where they are situated within this broader network. So because we violate so many assumptions with like network data, we need different approaches for doing statistical inference with networks. And we're going to talk about those. Basically, we'll talk about it. I'm getting way ahead of myself. So anyways, we're going to talk about like core concepts. We're going to talk about applications for these different statistical approaches. We're going to look at some specific questions, research questions that we can answer with network modeling. And then we're going to look at one specific example from the literature. And then we're actually going to do a little bit of this network modeling ourselves. All right, so just a quick refresher, like network vision, there's kind of like two things that we commonly do to describe networks. I would wager like maybe about 75 to 80% of articles that have been published about network analysis, applying network analysis in educational context, is primarily focused just on descriptive, either descriptive stats or descriptive depictions of networks through visualization. So like, what does this network look like? What are some core features of this network? How do we describe this network mathematically using numbers like density or reciprocity or other things? And that's like the bulk of network studies that I think even today you'll still see. But sometimes we get to a point where we want to move beyond that. And we might see features of our network that we want to be able to say, hey, these features, like, why are these groups of students that are clustered together? Like, it seems to be that all these students or these teachers that are clustered together in this network, like, share these characteristics, like either they're share a characteristic like gender, or maybe they share achievement levels. And there's ways to test for that. So Justina, for example, like in our student data or in this network that I'm working with here at NC State of this network of networks, one characteristic we're already seeing is that there's a lot more collaboration within institutions that are part of this network, just geographically located, than across other geographic locations, which is like fairly intuitive and makes sense because it's easier to collaborate with people who are closer to you. So we're going to be able to like test things. We're going to be able to formulate hypotheses and actually do some formal testing of those hypotheses through various network approaches. Just a refresher and pop quiz. Does anybody remember what reciprocity is in a network?
Yeah.
Oh, Somni, was that you?
No.
Oh, sorry, I don't mean to pick on you. So remember, reciprocity is like when we have ties between
Two-way.
individuals. Yeah, those ties can go like two ways. So if we talk about friendships, like I might say Justina's my friend in a network survey that a researcher conducts, but she might not say that I'm her friend. So that friendship tie is a little suspect from the beginning. If two
Question,
people don't.
is it theoretically correct to say bidirectional?
Yep,
Okay.
absolutely. And one of the things that we basically, for the most part, these selection models that we're going to talk about, like why do some people have ties with other people in this network? One of the things we almost always build into these network models just by default is reciprocity, because it's such a core feature of social dynamics. For example, if we're looking at interactions in an online discussion forum, it's very likely to be the case that you are going to respond to someone, more likely to respond to someone if someone has responded to you in a discussion forum, whether within the same forum or if it's a course like across the course. And we find this idea, this notion of reciprocity, almost like a given for networks. So it's something we always want to control for when we're putting together network models. All right, so just some refreshers. These are not refreshers, this is new information. But I'm going to talk about like, forgive me, I'm refreshing myself too on this material because I'm going to teach it this semester, but it's been since the summer since I last revisited it. Oh yeah. So one of the aims of this network modeling, what we're trying to accomplish by going beyond just showing a network graph and describing like network measures for a network, is basically we're trying to make inferences about these networks. So we might be using it to examine relationships within a network, like why someone is connected to someone else. We can use it to test hypotheses, like I just said before, and more advanced network models can actually look at changes in network over time to see if there's like statistically significant differences in how a network looks at one point in time and how a network looks at another point in time. Justina, this is very useful for evaluation purposes because any sort of initiatives that might be focused on pure collaboration or collaboration among institutions or groups, sometimes we'll take like a baseline measure of those network and say, here's what collaboration looks like among these colleagues right now. But the goal of this initiative is to like improve collaboration among these groups so that like 2 years from now, we see a lot denser network and we see more ties between individuals. And there are ways we can actually like statistically test whether or not this network is more dense just by pure chance, or it's beyond like just what we would expect to see by chance. And the way we do this in network analysis, this is a little bit, oh, forgive me, we talked about this already. In order to do inference with network data, there's a number of obstacles that we face. Some of you have mentioned these already, the violation of like core assumptions for statistical inference for traditional models. Assumption of normality, assumption of independence. So we have to get around those things. Also, conventional formulas just don't apply for types of network data, as you guys have already seen working with network data. Working with things like matrices and edge lists and the way we store data is very different than how we store traditional data. And then one thing that's really interesting about networks too is networks aren't necessarily like static things. It's typical for networks to change over time. In some cases, there may be like a lot of consistency, like if we're looking at friendships in elementary schools, we might see like consistency of friendships over time, but there's always like an expectation that networks change. So within the network analysis world and within like statistical inference world for networks, there's been a lot more work done on models that incorporate changes over time for networks too. I haven't personally used any of them, but I know it's like an evolving space in network analysis. So any questions so far? Because I've done a lot of talking. All right. If not, I'm going to move on really quickly to the next thing. So inference to networks. underlying most of these network models is this idea of sort of, some of you can probably describe this better than me, but this notion of mathematical permutations of matrices. So if you remember network data, we often store it as a matrix, right? So in this case, we could say, I forget the context for this, but I think this is a collaboration network among teachers in a district. And in this case, we can see that teacher 1 has a relationship with teacher 3. And I think in this case, the 1 through, I think it might go up to 5, is the strength of that collaboration as reported by the teachers themselves. But as you can see, we store networks in this matrix format, or they can be stored in this matrix format. So when we're trying to test hypotheses about, is this network different than this other version of this network that we would expect by chance, what effectively most of these models do is they take these matrices and they rearrange them randomly given a set of parameters. And they create this sort of space that exists of like 10,000 variations, random variations of these networks, given certain parameters like number of connections between individuals and other things. And they say, what is the likelihood that we would see these characteristics in this network, given all of these random permutations of this network? What is the likelihood we would see these characteristics by chance? As you can imagine, if you have a network that's like 30, 50, 100, 1,000 actors in your network, that is, it's computationally very intensive. So most of these network models didn't really start developing and coming into use until about, I would say, 10, no more than 20 years ago, because the computers that could actually run them just weren't powerful enough. Like now I can run most of these models just on my MacBook Pro. But when I was doing my dissertation, I actually had to put together a computing cluster on Amazon and let these models like run overnight. And I was only like running some exponential random graph models on these teacher networks. And there were like maybe like 3, no more than 500 people in these networks. And that was just like in 2014, I think. So like less than 10 years ago. But now I can run those same models that I did for my dissertation, like on my MacBook, basically, just a basic laptop. All right, so all of this is in the readings. I'm not gonna like go over every single thing, but these are like some typical questions we might be able to ask and answer through statistical inference with networks. Like relationship between how much people collaborate and whether or not they have other ties within each other. So are people who share confidential information with each other more likely to collaborate as well? And we would have like 2 different networks, a collaboration network and a confidential ties network. And then we could test to see if there's a relationship between those 2 types of ties. Some of these models are very network focused, which for me often as an evaluator is not super useful because we're more interested in outcomes. But some of these models are really focused on outcomes themselves. And these are things called, Josh Rosenberg has done some of this work too. Diffusion models look at more outcomes, but it's influence models. So like, does having ties, for example, let's say Justina and Sunmi and I are in like the poor academic group. Does having like ties with other students who aren't performing well academically, like more likely to not enroll in college or something like that? So we can also use some of these models to look at, does someone's position in a network or someone's characteristics of their, being a part of that network, does that influence outcomes at a later point in time? In some of the famous network studies, I'm trying to think back, there was like one maybe like 10 years ago about how friendships and smoking is effectively like contagious. Like if you had more friends that smoked, you were more likely to also then become a smoker. So I'm going to skip this discussion part so we can get to actually some of the analysis part too. So there's like a few common types of models. There's the QAP model, qualitative assignment procedure, and that's to talk about just what we had talked about before, like are ties in one network associated or correlated or related to ties in a different network. And it could be like ties at different points in time. Like if I have ties with people who I collaborated in year one, am I also more likely to have ties with them, collaboration ties in years 3? Or I could relate them to other types of ties as well. But that's like inward focus. That's focused on like trying to test hypotheses about the network structure itself.
I have a question. This
Yeah, go ahead.
QAP, I'm not familiar with this. So, for example, there is year 1, year 3, right? So,
Oh, yeah.
Yeah, same. Is it same group or?
Same group, exact same group. Yep.
Right.
And what we'll talk about, we have an example of a study, Sami, that we're going to talk about in a little bit more detail about them using this specific procedure to look for differences between, because there was an intervention that took place in this school.
Right. Mm-hmm.
Yep.
So what if there is someone moved to another school? Do we need to remove that because it's a density or other degree?
We would, yeah.
It's
Yeah. There's a whole host of data quality issues.
Right.
For this. Yeah.
I see.
And how we deal with missing data in networks is a little different than how we deal, because we can't like, for most network data, we can't do like imputation or something like that, where we would try to guess like that person's relations or state of things. So often the way of dealing with it is removing those individuals from the analysis altogether. But that does present problems, right? And school turnover, teacher turnover, and especially leadership turnover in schools and districts right now, like being at like all-time highs, that does create problems for network researchers.
Okay, thank you.
So really good question. This other one, it's a more advanced model of a qualitative assignment procedure. Ooh, 1052, I'm sorry. I'm gonna rush this a little bit more. This one's more sophisticated and allows you to incorporate like, think of it as like ANOVA or something instead of just like straight up regression analysis, where it allows you to incorporate like multiple types of ties within a network and run like different models. So I'm not explaining it very well. I'm going to reference the chapter readings that I'll share at the end, and they explain these models much better than I can do in like 5 seconds. The one we're going to focus on today are these P-star models, and there's a whole host of different types of these, but we're going to focus on these exponential random graph models. And it might be a little bit hard to see right now. I'll see if I can make this a little bigger. But these are these kind of selection models that I talked about. So let's see, Larissa, for example, Larissa might have a, or Melinda, actually, we can take your example. So these like peer mentor and support type networks and who goes to who. Like one things that we could test for is whether or not like gender makes a difference in who they go to for support. Like, do we tend to find that like females often will go to other females for certain types of support or for support in general? Or it could be other things like other characteristics of individuals. Here, in this example, this is again from that study that, gosh, what is it? Alan Daly at University of San Diego and another group did. But they were looking at like, what were the best predictors of who would exchange confidential information, who you felt secure talking to within a school district among other people in your district. And one of the things that they found was the reciprocity. Like if I confided in Justina, there was a much greater likelihood that Justina would also confide in me as well. So reciprocity is like a core feature of networks on who's going to form a tie with who. In this case, what they found was gender didn't really make a difference. Like whether you were male or female, it didn't have any sort of influence on whether you sought out other males for confidential exchanges. But what they did find when they incorporated efficacy in this model is whether or not in this district you perceived someone as being more, in this case, the reform was around, gosh, it was like innovations and technology in the district. So whether you perceive them as being more of a leader in this space, then you would more likely reach out to them for confidential support. So, and this was like what I did for my dissertation work too. We were looking specifically at online discussion forums, and we're trying to figure out like, how do we get people talking to each other more? And one of the things we wanted to do was like, well, let's figure out like why people talk to each other now. So we looked at a whole host of characteristics and ran these models and tried to figure out like the best predictors of whether someone was going to reply to someone else in these discussion forums. And we looked at like data from an entire group of massively online courses, and we found a few key characteristics. One was reciprocity, no surprise, played a huge role. But second was really interesting was geographic location. And what was really interesting about that finding is people didn't necessarily tell other people where they were from. And yet there was still like a greater likelihood that people from the same region and even the same state were more likely to find each other in these online spaces and like talk to each other about school reform efforts, which was really interesting. And maybe it's because they're dealing with similar issues because they're in the same region. Maybe there were things like just cues in a discussion that like let you know someone is from Michigan and then you like feel compelled to respond to them. And then for like traditional things, if we're looking at, if we want to take like core features of, let's say someone's measure of centrality, like degree, like how connected they are to other people in the network. And if we want to see if that's related to some outcome we care about, like student achievement or enrollment in college or enrollment in like high school CS courses, things like that, then we can do like traditional regression type models, but ones that are specific for working within networks. All right. So I'm going to run you through really quickly. It's 10:57. If you have to go at 11, I completely understand. But remember, all these materials are here for you. They're in that GitHub site. And then if you go to the end of these slides too, I link to everything as well. So at the very end, I link to all the readings where the information goes into much more detail that I talked about today. And then there's also a case study for you as well, including the study that sort of guided the case study that I developed for this. And it will walk you through in much greater detail than we do in this little code along of how to do like a very basic exponential random graph model for network data to predict like why people form ties with other people in this network. All right, so if you want to follow along, we're going to do a code along now here. So in our code along, we're going to try to answer like a really, really basic research question. And we're going to take the information from this study that Alan Daly and his colleagues did that was looking at this school reform efforts that was part of, this was way back in the No Child Left Behind era. And they collected ties or relationships on a whole host of things. Who you went to for knowledge, who you went to for advice, like who you perceived as innovators in your school and district. But what we're going to do is something very basic. We're going to say, we're going to try to test a hypothesis. We might think, for example, that like one major influence of whether someone is going to exchange confidential information with someone else is they might feel more comfortable talking with someone of their own gender, for let's say. And we can actually test that, and we'll take a look at to see if it actually like shakes out within this network that we see of confidential exchanges. A really easy to understand version of what we're going to do today is, Melinda, I think I might have shared this at the summer workshop, Grey's Anatomy, yeah, network ERGM. I wonder if this site still exists. It does, yeah. So someone used the same modeling technique, but I don't know who put this data together, but they collected data from the Grey's Anatomy TV shows on who hooked up with who. So basically who slept with who. And what they ended up doing was, so here's what the network looks like. And this is like over, I don't know how many seasons of Grey's Anatomy. I've never watched a single episode of Grey's Anatomy. But you can see like this is what the network of hookups look like on the show. Sloan, is Sloan a male or a female? I'm assuming a male. Blue's a male.
He's a male.
So Sloan apparently on this TV show was like very active.
Yeah.
And then what we can do is like we can try to figure out characteristics of individuals in this network that might have influenced whether or not they hooked up with each other. So gender might be something we test for, and we would see like gender definitely was an influence, but we could test for other things too. Like, let's see, what's so special about Sloan? Like
His nickname is McSteamy.
So like their level of handsomeness or something, like their attractiveness or something like that.
Yeah,
And that might influence.
He's an orthopedic doctor.
Yeah.
Oh,
So what? Yeah. So what they found with this one is, I'm sorry, this is like way more information than you want.
The trouble is this started when I was in college, so it was like one of those college shows that we always watched, right?
But this is basically what we're doing. It's like not who hooked up with who, but like who went to each other for confidential information, and like what characteristics about those individuals likely might have influenced who they go to for support. And then what we could do is we could take that information that we learned from that and use that to help guide or facilitate more people seeking support or advice or knowledge or things from other individuals as well. All right, so first thing we're going to do is we need to create a new R script. So let's go and create a new script. And we need to load some packages. So we need to load a few packages here. So I'm going to type library, and I'm going to load the read Excel package. Does anybody know why I'm loading that package?
So we can read the Excel file that has all the data in it.
Our data is stored in an Excel file, which is not uncommon, especially if you're working with schools and districts. We need to load our ERGM package, which lets us do our network modeling. And we need to load our StatNet package. And the reason we're going to load that one is, do I not have StatNet installed? Let's see. Oh, I have StatNet. And we need to load the StatNet package. So let's go ahead and load this package. And with those three packages alone, actually the main one you really need is the ERGM package. We can do some network modeling just like our Grey's Anatomy. And we can try to make hypotheses about like why people connect with other people. So we'll get those packages loaded and we will move on. All right, I'm going to save you guys some trouble. So if you click on the slide here, you can just copy and paste that right into your script, and I'll put it in the chat window too. Oh, Justina needed to go. I will follow up with Justina and thank her for joining. So I'm going to copy the code in the chat window too. And we're going to load some data. Load some nodes. Oops, this is error. It doesn't exist in our current directory. And I'm going to explain why when you get that error. Because the folder, the data file that we're looking for is in the data folder, but it's actually in our unit 4 data folder. So we're going to add that little prefix to our file path. And then does not exist. Ooh, boy, what did I do wrong? Oh, it's a lab 4. Sorry, I'm thinking unit because in my course I call these units, not labs. Lab 4. There we go. And lab 4. run that. And I'm going to copy this for you in the chat window too. So now we've got our data. And if we look in our environment, we can see that we have our leader edges, and we can take a look at that. So that's our edge file. So we can see that leader number 3, we removed all their names intentionally, had a confidential, or noted that they went to school leader number 1 for confidential exchanges of information. So that's our edge list, and we can also look at nodes. So these are some things that we're going to test some hypotheses about, as whether or not they predict whether someone exchanges confidential information with someone else. So we can test their gender. We can test whether they're at a district level or a school level leader. So a principal versus like a superintendent, for example. And then there was a survey that was administered to them as well. This trust score, basically, if they had higher scores, higher levels of trust, that means they felt more comfortable as a whole with, gosh, I can't remember, forgive me, I don't want to misstate. It was something like they, oh, goodness, I'd have to go back into the reading, but it was something like trust in the competency of your peers maybe, or trust in something like that. And then there was also like a efficacy score, like I think this was more inward, like how effective do you think you are at doing certain things? But I could be wrong. I'm probably misstating those. But anyways, like there's a survey that is administered to get some other like characteristics about these individuals. And what we're going to do is see if we can see if like something like gender or something like school or district level is a good predictor of whether or not someone went to someone else or had a tie with someone else about confidential exchanges. And it's as simple as that. So we take a look at the data, we'll skip that, talked about those things already. So let's move on.
So Sean?
Yeah.
I don't know if other people are getting the same error message, but you loaded in read Excel, but then the files are CSV files. So I'm getting a can't find read CSV.
Oh, forgive me. You are totally right. Now I have to go back and fix this.
I don't know how yours work though.
It's because I think I already have the tidyverse package loaded.
Okay.
Yeah, so forgive me. Load
Tidyverse.
Yep, tidyverse. And then it will load, tidyverse has a ton of packages. It will load automatically the read R package, and the read R package has the CSV function. Thanks, Belinda.
Oh, well, I'm still fighting with the.
Yeah, there it is, the read R package. That's what loads CSV files. And thank you, that actually let me know that I'm going to need to change these slides, not just for Laser Institute, but for my course as well, because otherwise people are going to get confused. All right, so let's go back. Hopefully that works for you now. So the next thing we need to do is we have these nodes. There they are. We have the nodes. So these are the people in our network and characteristics about these individuals. And we have who's connected to who in our network. But before we can do any sort of network analysis, we have to effectively, especially for if we're using characteristics of individuals to predict whether or not they form ties with other people, we have to fold them together into a single data object. And in R, this is some form of network object. And there's lots of different types of network objects. There's like table graphs, which is one form of network object. There's a network object called network, but basically what it does is it takes our node data and it takes our leader, our edge data, and it combines them into a single file or a single object type. But as you can imagine, like there's no way we can easily store in a normal file, like a normal spreadsheet, information about who's connected to who and information about characteristics of those individuals. So if you try to envision like how you might store this data in a single spreadsheet, It's just not feasible in a way that I can think of. But what this function does is, here, we'll run this. I'm going to copy this. What this does is it takes our edges and it takes our nodes and it's going to turn them into a network object that we can use. And this as network objects, this function that combines our edges and our nodes into a single network object, this is, I'm pretty sure, from the StatNet package, and that's what we loaded that for. But once we have those connected and loaded, let's take a look at our network. So now that we have them combined into a single network object, we can see our network has some basic descriptives about our network. There's 43 people in our network. This is a directed network. So I might be friends with Damji, but she might not be friends with me. So I might have named her as someone I go to for confidential information exchanges, but she may not have named me. We can also see that there's no loops in our network. Hopefully, Melinda, you don't have to deal with this, but sometimes it's possible where people name themselves. So like students might do this on a survey, like who's your best friend? They might say like, I'm my best friend. Or more likely, if we're working with like online discussion forum data, like Discord, like conversations on Discord or Slack or something like that, it might not be unusual for me to reply to one of my own posts just as a follow-up. But in the network data, it's going to look like I have a connection with myself. And those are called loops. So that's basic information about our network. This is something to take note of. Different network models and different network packages prefer their networks in different ways. So what I'm going to do is show you this. And look at the class of this object, this leader network. And we're going to see that it's a certain type of network object. And this is a network type of object. But there's other ways you can store edges and nodes together, like table graphs, or gosh, there's another one. I forget what it's called. But the ERGM package that we're going to use for network modeling, it only takes networks that are the network class of object. So just something to like have on your radar. All right, so we just checked the class. So now we have a network object and we just viewed our network. And you can look at your network just by typing the name of your network and running it. If we tried to view our network over here, so here's our leader network right here. If we try to view this, we'll see that it's stored in a way that R likes to store things. So it's like a collection of different lists that are stored together and bundled together, almost like a little mini database that it puts together. All right, so we've got our data. We've turned it into a network object that our ERGM package will recognize, that R recognizes. And now what we're going to do is create our first network model. And remember, what we're trying to predict effectively with these ERGM models is what best predicts why someone connects with someone else. And is it something like gender? Is it something like whether they're a district leader or a school level leader? And we could have it like, we can make hypotheses or predictions about whether school leaders are more likely to connect with school leaders, or it may be intuitive us to think that school leaders are going to be more likely to connect with district leaders. And we can add terms or parameters or basically our predictions to our model that we can actually test. And what we call these, basically the formula is like typical regression formula as well. So what we're trying to predict is the ties in our network. And then these are our predictors, basically. And we can include as many predictors as we want, but the more that we include, like the more computationally intensive it is to run. And like once you get past like, I don't know, 10 terms, depending on the size of your network, it can run really, really slow and even potentially take all night. So be very selective about like what you truly think are the best predictors of the ties in your network. So what we're going to do is we're going to run our very first model. So I'm going to copy this in here. And I'll create some space here so it's easier to read. And the first thing that we're going to do is we're going to use this function that's just built into R called the setSeed function. And what this allows you to do is if DOMG wants to run my code and reproduce the exact same results that I got, she would run the setSeed with this random number. I picked 589. It can be any number you want. I picked 589 because that's like the course section of the SNA course I teach. So the first thing, just for reproducibility purposes, is we'll set that seed to a certain start point for running our models. All right, and now this is like our baseline model. This is what we're probably going to include in any sort of selection model where we're predicting ties, any model that we're going to run. It's like our standard base model. And what this controls for is it controls, oh no. Hey, okay, I'm back. What this controls for is, oh, but I did lose my slides. It controls for how many ties are in our network. So Melinda, I don't know if you remember where we talked about those permutations, where we're basically, when we're running these models, what we're effectively doing is taking that matrix for a network and we're creating like 5,000 or 10,000 random versions of this network to see if just by chance, these things that were predictive occur more than we would expect by chance. So what we're going to control for here is that when we run these random versions of this model, that these random versions of this network that we're running have the same number of ties as all the other random versions of the networks. So we're controlling for like how many ties are in our network. And then the next thing that we're going to control for is reciprocity in our network. And we're going to run this model and we're going to see that reciprocity is something that's statistically significant, a significant predictor for ties in our network. We're going to go ahead and run this. And you're going to see basically it's running through different versions of your model. And it's gonna, what we've done right now basically is you're not going to see any output for our model yet, because all we've done is create, we've created the, I don't know how to explain it, like the object, the shell for this model. And we're going to use something called the summary function to get the stats from our model that we just ran. So if we run this, we're going to get our statistical output for this model. So who can tell me, just looking at this, kind of think about it, interpreting it as like you might interpret a traditional regression model, where like the number of asterisks that you see for the p-value is indicative of occurring greater than you would expect just by pure chance. So the number of edges, just ignore, because that's always going to be statistically significant. One thing to note, though, is do you see how it's a negative value? That means in this network, there's just not, how do I describe this? There's not a natural inclination for people to just form ties with each other just randomly. It's indicative that our network is kind of sparse. That means like there's not a lot of connections between individuals. So just that negative sign means that your network is not very dense at all, very sparse network. And the higher that number is, like the more sparse it is. The mutual, though, anything that we see that's positive for these estimates means that it increases the likelihood that someone is going to form a tie with someone else. And we can see that reciprocity. So if I named Larissa as my confidant in the school district, it's much more likely that she is also going to name me as her confidant in this school network. And we can see that's statistically significant as well. So it is very, very normal in any sort of network that you're looking at that's bidirectional, that's allows for directionality in the ties. It's very normal for that to be significant. It would be unusual if reciprocity didn't play a role in network ties. It's just a common social phenomenon. I'm going to run my, forgive me, just so I have them for reference. Let me get my slides back. And Melinda, we're going to wrap up pretty soon, so we will have time for office hours, so don't worry. Running the slides. You can see right now on my slides, it's actually running those network models. And here we go. So that's our very first model. That's our base model. Again, like this is not like terribly sophisticated. One thing as we keep like adding predictors to our model to know is that like within network, there's not only predictors about the characteristics of individuals, like my gender or my sense of trust or my socioeconomic status. There's also other types of predictors specific to the network itself. So one type of predictor is something called like a popularity effect, where within this network, someone who's more central to the network, it's the Sloan effect. So think of it as like the Grey's Anatomy Sloan effect, where there's a certain person who seems to be like a black hole for ties for other people. There's other things that you can test. This reciprocity, the mutual thing, that's like a network predictor. So there's characteristics of the network itself, independent of the individuals, that might be influencing tie formation within the network. So those are called network terms. And then there's like individual specific terms as well. And in the ERGM package, there are tons and tons of different terms that you can test for. So see everything here that basically says like ERGM terms. Like these are all different network characteristics that you can test for. Term. There we go. And there's a lot of characteristics that you can test for. And we're only going to scratch the surface today. But usually what we most care about, usually the only thing we include those network terms in for is to like control for network effects. Things that are common social phenomenon that we want to weed out to see if it really is gender for why people connect with each other and not something like reciprocity. All right, so now we're going to build our next model. And in this model, here, we'll copy this and we'll go over here. In this model, we're going to add another term. So we're controlling for the number of edges. We're going to control for reciprocity or mutuality in our network. And now we're going to make some predictions here. I'm going to rewrite this code so it's a little bit easier to see. I'm going to put plus mutual, plus node match, plus node match. So now we're going to test for something else. Now we're going to test for something called, have you ever heard the term homophily? The expression of birds of a feather flock together. So people who share similar characteristics are more likely to connect with another. And we're going to test that. We're going to see like, are males and consequently females, are males more likely to connect to males and females more likely to connect to females? And is someone at the district site, the district level, like superintendents, more likely to connect with other people at the district level? And conversely, are people at the school level more likely to connect to people at the school level? So now we're making some new predictions. So we're going to test for reciprocity in our network. We're going to test for 2 types of homophily, whether gender is a factor and whether school or district level is a factor. Before I run this model, any predictions? Does anybody think gender will be statistically significant?
I don't think so.
Nope. Well, you sort of got a sneak peek and like earlier where gender wasn't a factor.
But district could be district side.
I can't remember the outcome, so your guess is as good as mine. My guess though is district versus school level. I think that is a predictor because just physically you spend more time with those, well, in like a sort of hierarchy within districts too, like shared concerns, shared issues. I'm more likely to reach out to a principal if I'm having an issue that's like related to my school than someone at the superintendent. So I think that one's going to be significant.
I think part of the problem is if you start looking at gender at the different levels of schools, you're going to find so many more females at the elementary level.
Yep, that is
I think-
definitely a confounding factor.
So I think that's just going to end up making gender not significant.
Yeah, and as a former elementary teacher, that is definitely very common. I was often like one of the only male teachers at schools that I worked at. There's usually like maybe 2 others at the schools. All right, so let's run this model. First, we're going to fit our model. So I'm going to run this. And now you can see over here, what's going to pop up is our ERGM model number 2. You all probably already know this. We could name this anything. We could name it like Bart Simpson. We could name it, like, it doesn't matter what you name it, but try to name things that describe what they actually are. So this is our ERGM model number 2, and let's get our summary stats now. And what do we find? So gender was not a significant predictor. So male to male, let's see. So conversely, like female to female too. You can also test for the opposite. Like in that Gray's Anatomy network, we could test to see if it's more likely that a male is going to hook up with a female for like the Gray's Anatomy example. So you can test for whatever the opposite of homophily is, a heterogeneity or something like that. But look at our district sites. Those at the district site level were more likely to connect with others at the district site level too. And then we could just throw in more things to our model as well. Oops, sorry. Oops. Let's test our final model. This is our 3rd model. All right, our 3rd model, we're going to add a couple new terms. So we've got mutuality. We've got testing for homophily among males. We've got testing for homophily among districts. And then now we can also see this is, instead of a node match, like male, male, female, female, this is like a node covariate. So do people with higher levels of trust, are they more likely to connect with other people with higher levels of trust? So this is a way we can account for numerical values as opposed to categorical variables. All right, any predictions? You think trust is going to play a factor in who you confide in? My guess is yes. I would think that's likely to increase the likelihood that you're going to connect with someone else who also has high levels of trust. Or if you're more cynical, so let's test this model. We're going to fit our model first. It's going to run through, this is basically running through, remember I told you how it creates these matrices and then it creates random versions of all these matrices. That's effectively what it's doing over and over and over again. All right, so we fit our model. If you have a really big data set and you're running a ton of parameters, this happened to me a lot on my dissertation, is you may run into issues where your model just fails to converge, which some of you might have run into with just like normal data analysis too. And if that is the case, there are ways to deal with it, but it's probably not going to be something a situation you come across. So let's look at our stats and read our basic output. So reciprocity, yes. Node match male, no. District site is still a yes, but trust was not a factor. So people with higher levels of trust, it didn't influence whether they confided in other people with higher levels of trust. So that's basically an illustration of like one type, only one of like many different types of network models. And this network model is focused on selection. So how we pick the peers that we have ties with. And sometimes we don't pick them. Sometimes the network, like network factors, influence us without us even knowing. But sometimes we might be intentionally or consciously forming connections with other individuals because we share same characteristics. Like, you know, maybe high school guys who love basketball, you know, becoming friends with other people who love basketball, whatever it happens to be. All right, and I do encourage you, because I did not do the best job of explaining everything today, these 2 chapters from that Carolyn reading, they explain this in much greater detail and much more comprehensively than I did today. And if you want to, this case study, basically this code along that we did, there's oh, curses, seriously. All right, hold on a second. Case study 4, SNA lab, case study key. So it's right there. Oh, whoops. Dope. Lab 4, SNA lab, case study. Oh, whoops. Case study key. And I will have to fix that link as well. There we go. In this, in your files here, there's a case study. And if you want to practice some of this, I go into a lot more detail about, and more coding stuff too. A lot more detail and more practice with a lot of the functions and the code from our code along too. And I give a little bit more information about the study where we pulled this data from. And if you get stuck, there's also an answer key for the case study as well. And this is a pretty fun activity too. It's just a longer version of what we did right here with a lot more explanation of everything. All right, well, that's it. Thank you so much for being a good audience. And let me go to the thank you slide. And thanks for sticking over the, I'm sorry, we spent a lot of time on just catching up at the beginning of this. So thanks for doing that. I'm going to stop sharing. And I'm going to stop the recording too.
Sean, I have a question.